Recall that for all linear systems, the total system response is the sum of two responses. One is the response to the initial conditions, which is referred to as the zero input response. The other is the response to the input, which is referred to as the zero state response. We'll start our analysis by looking at the zero input response of our linear time invariant continuous time system described by the differential equation. So now we'll look at how to find the zero input response for our differential equation. Now for the case of the zero input response, the input x of t is 0, and therefore the governing differential equation simplifies. The terms on the right-hand side, p of d times x of t, becomes 0, since x of t is 0. So now our differential equation can be written as q of d times y0 of t equals 0. We've added the subscript 0 to indicate that we are finding a particular solution of our system differential equation, the solution where the input is 0. So now we'll expand out q of d to see what's going on. And you see the polynomial here inside the curly brackets, multiplying y0 of t. Of course, that's equal to 0 in the case of zero input. What is this equation saying? It's saying a linear combination of y0 of t and its derivatives must be equal to 0 at each and every time. How is it possible that a function plus its derivatives can be added together to equal 0 at all times? This requires that the derivatives of the function are related directly back to the function. The exponential function e to the lambda t has this particular property. The derivative of e to the lambda t would be lambda e to the lambda t. In other words, it has the same functional form as what we started off with. So e to the lambda t seems particularly promising as a solution to this differential equation. Let's plug this into our differential equation and see what happens. So we'll let y0 equal c e to the lambda t. The c here is just an arbitrary constant. And now we'll take derivatives of it. Now the first derivative is dy y0 of t, and of course it'll come out to be lambda c e to the lambda t. And then when we take further derivatives, we'll just get higher powers of lambda multiplying c e to the lambda t. The second derivative of y0 would be lambda squared c e to the lambda t. And the nth derivative of y0 would be lambda to the n c e to the lambda t. Now we'll take all those derivatives and y0 and we'll plug them back into the differential equation. When we do, here's what we'll find. Lambda to the n times c e to the lambda t plus a1 lambda to the n minus 1 c e to the lambda t plus and so on to an c e to the lambda t equals 0. Now we can group the terms together to simplify this. We'll find a polynomial in lambda multiplied by c e to the lambda t equals 0. The polynomial will have the coefficients that were in the differential equation, a1 through an. For this equation to be satisfied, we must have the term inside of the square brackets equal to 0, since c e to the lambda t cannot be equal to 0 at each and every time. Since the polynomial must be 0, this dictates certain values of lambda for the solution. These values of lambda are the roots of the polynomial within the square brackets. So here we're writing that polynomial out and setting it equal to 0. And we note that that polynomial is q of lambda. Recall that q of d was the differential operator polynomial which operated on y0. Q of lambda is called the characteristic polynomial, and it will be very important in the study of the zero input response. Now q of lambda is an nth order polynomial, and its nth order, since the original differential equation, had n time derivatives of y0. An nth order polynomial has n roots, so there are going to be n values of lambda that will satisfy q of lambda equal to 0. The end roots of this characteristic polynomial are referred to as the characteristic values, and we'll label them lambda 1, lambda 2, through lambda n. These numbers may be either real or complex valued. We can write the characteristic polynomial as q of lambda equals lambda minus lambda 1 times lambda minus lambda 2, and so on through lambda minus lambda n. Now, since each characteristic value makes q of lambda equal to 0, we know that each characteristic value will dictate a different solution to the zero-input differential equation q of d y0 of t equals 0. For now, we will assume that all of the characteristic values are distinct. That is, no characteristic value equals another characteristic value. That is referred to as the repeated case. Let's write out our n solutions to our linear differential equation with no input. We'll label them y01, y02 through y0n. y01 is equal to c1 e to the lambda 1t, y02 c2 e to the lambda 2t, through y0n equal to cn e to the lambda nt. You see we get one solution for each characteristic value, lambda 1 through lambda n. The c's here are just arbitrary constants. We'll solve for them later. Each and every one of these is a solution to our differential equation. So let's pick one, which we'll call y0 sub j. J here is an index, and it could be any value between 1 and n. When we plug this into the differential equation, we'll have q of d times y0 of j, and that must be equal to 0, since y0 sub j satisfies the differential equation. Since each one of these satisfies the differential equation with 0 input, we can write out the following. q of d times y0 sub 1 of t equals 0. q of d y0 of 2 sub t equals 0. Through q of d times y0 sub n of t equals 0. Now we can add all of these left-hand sides and right-hand sides, and we'll find q of d y01 of t plus q of d y02 of t plus through q of d y0n of t must be equal to 0. Rearranging this, we can write q of d times the term in the curly brackets, y0 sub 1 of t plus y02 of t plus and so on to y0n of t equals 0. That is, the term inside the curly brackets also satisfies the differential equation. This is in fact the most general solution to the differential equation with 0 input. The solution is y0 of t equals c1 e to the lambda 1t plus c2 e to the lambda 2t plus and so on through cn e to the lambda nt. That is, we'll do a combination of terms. Each term is given by e to the lambda jt, and we combine them together in a linear fashion with the coefficients c1 through cn. Now these coefficients are determined by the initial conditions of the problem we're solving. The terms e to the lambda it are called the characteristic modes, or simply the modes of the system. In this course, we'll often be talking about the modes, so you should know what they are. The modes are the general forms of behavior the system can display when the input is 0. When we solve a 0 input problem, we'll need one initial condition for each derivative of y0 of t in the differential equation. That is, if we have an nth order characteristic polynomial, we'll need n initial conditions. For example, let's consider the following problem. q of d is d squared plus 3d plus 6. Of course, q of d is being multiplied by y0 of t for the 0 input problem. This problem will require two initial conditions to be specified in order to solve the problem. The two initial conditions that are needed are the values of y0 at time 0 and the value of its derivative at time 0. These two initial conditions will give the coefficients in the general solution of the problem, C1 and C2. For example, if y0 were the position of an object and we had the differential equation that was second order as on the previous page, we would need to specify the position, y0, and its velocity, dy0 dt, at time 0 in order to find the zero-input solution. This situation is illustrated graphically in the figure at the bottom of the page. We give y0 at time 0 and its slope, the velocity, at time 0. Given these two, the form of the solution, y0 of t, will be determined. The zero-input response, in this case, will be the sum of the two modes, e to the lambda 1t and e to the lambda 2t. These are combined together with the coefficients c1 and c2. c1 and c2 are determined so that the initial value of y0 and the initial slope, dy0 dt, match the prescribed conditions. Let's now look at an example to illustrate this idea. And our example is the following differential equation. D squared plus 3d plus 2, operating on y of t, equals 4x of t. And we're to find the zero-input response, y0 of t, when the initial conditions are y0 at time 0 equals 2, and dy0 dt at time 0 is equal to 1. Since this differential equation is second order, we'll have two modes. And so we can write y0 of t is equal to c1 e to the lambda 1t plus c2 e to the lambda 2t, where lambda 1 and lambda 2 are the roots of the polynomial lambda squared plus 3 lambda plus 2 equals 0. When we find the roots of that polynomial, we'll find one root is minus 2 and the other one is minus 1. Now we'll solve for c1 and c2 using our initial conditions. y0 at time 0 is equal to 2, and dy0 dt at time 0 is equal to 1. So, we know that lambda 1 is minus 2 and lambda 2 is minus 1, so y0 of t is c1 e to the minus 2t plus c2 e to the minus t. Setting t equal to 0, we find y0 at time 0 is equal to c1 plus c2, which is equal to 2. We'll label that equation number 1. And then we take the derivative of y0 of t with respect to time, and we find that's equal to minus 2c1 e to the minus 2t minus c2 e to the minus t. We set t equal to 0, and we find out that derivative at time 0 is minus 2c1 minus c2, which must be equal to 1, since that's the initial condition on the derivative. We'll label that equation number 2. Now we'll solve equations number 1 and 2 for c1 and c2. That's two equations and two unknowns, and we find the solution is c1 equals minus 3 and c2 equals 5. And therefore, the response of the system to the initial conditions, the zero-input response, is y0 of t equals minus 3 e to the minus 2t plus 5 e to the minus t. In our next lecture, we'll continue to examine how to find the zero-input response for a linear system described by a differential equation. The problem tackled in that lecture will be more difficult because the characteristic values will be complex.